Hi everyone, I hope you're doing well. We've been talking about semiconductors and semiconductor devices, and today we're going to talk about the most important semiconductor device in the world, which is the transistor. So I'd like to introduce transistors today as switches. So transistors are essentially solid-state electrical switches. We'll talk about the two types, field effect transistors and bipolar junction transistors. And after that, probably tomorrow, or in our next lecture rather, we'll talk about a little bit about commercialization of transistors and Moore's law, the state of transistor technology now. Okay, it should be really interesting. So hang on. Here, 1 second. Okay, so just to remind ourselves where we are, we've been talking about semiconductors, of course, and semiconductor devices. In the last few lectures, we've talked about diodes, and we've seen how the p-n junction, which is an interesting bit of physics in itself, is behind two important devices. Well, diodes that are used in electronics, but also light-emitting diodes, which are the cheapest and most efficient light source available today, and solar cells, which are rapidly changing the energy production in the United States and in the world. At least that's what we hope, right? So today we're going to talk about another extremely important semiconductor device called the transistor. And we're going to talk about a transistor as a switch. A transistor we can think of as a control that allows us to control a flow of current with an electrical signal. Okay? It's not always immediately clear why we need to do this, but maybe this picture helps make it clear. Suppose I have a large flow of current, a source that can provide a large flow of water, like a hose, okay? And I'd like to be able to turn the flow of water on or off. And I need some kind of switch that can interrupt it, okay? And the transistor is this thing. By applying a little bit of work or a little bit of voltage or a little bit of current, we can switch on and off a very large current. It's that gain that makes a transistor useful. Okay, in any event, I'd like to show you three devices today. The first, just to help get us grounded, is an old-fashioned thing, a vacuum tube triode. Okay, and we'll see how this works as an electrical switch. And that'll help us, I think, to understand what's going inside of a field effect transistor, and then next a bipolar junction transistor. Okay? So here, let's take a look at the vacuum tube triode, shall we? So here's a schematic picture of a vacuum tube triode. There are three important items in this vacuum tube. There's a filament, which is a source of electrons. When this filament is heated up, electrons can be emitted. There's a grid, which is going to control the flow of electrons, and there's a plate, which is where the electrons end up. Okay? So this is a three-terminal device. We have the filament, that's one terminal. Well, actually two, because we need to pass a current through the filament to get it to be red hot. And then there's the grid, the control, and then there's the plate, where the electrons end up. Okay? So in a vacuum tube, these would be filament, grid, and plate. But when we talk about transistors, the same functions will have different names. The source of electrons will be called the source, or the emitter. The control will be called the gate, or the base. And the anode of the circuit will be called the drain, or collector. Okay? All right. Well, let's see how this funny-looking device works. Imagine the following. Here I have the filament, which is heated up so it's emitting electrons. Okay? And suppose the filament is at 0 volts. Then we have a grid. Let's suppose the grid is at a voltage of plus 100 volts. Of course, electrons then would be attracted to the grid, and they would accelerate across this potential difference of 100 volts. Okay? Likewise, in this circuit, the plate is also at plus 100 volts. So electrons that are emitted by the filament and accelerated by the grid will either stop at the grid, or for the most part, they'll continue on until they hit the plate. So now I have a current of electrons going from the filament to the plate. This is a switch, and the switch is on. Okay? However, if I change the voltage on the grid, I can change the state of the switch. So if I change the voltage to minus 100 volts, then electrons will be repelled by the grid. Since they never reach the grid, they also never reach the plate. And so the current between the filament and the plate is switched off. So I have a switch, off, on, off. Notice this is a rather nice switch. It has no moving parts, nothing to wear out, except maybe the filament. Okay? All right, well, that's a voltage-controlled switch. And when we start to talk about transistors, it might help you to have this device in your mind. Okay, well, let's go on now and talk about the first type of transistor, the field effect transistor. Okay? Here's a schematic diagram of a field effect transistor. This is what it looks like in a cutaway picture, I guess, in a cross section. This is what a schematic diagram might look like in 3 dimensions. This is an actual transistor all packaged up. Of course, this is a very, very large transistor, which is used for switching on and off large electrical currents in the order of amps. Okay, let's go through and talk about the different parts of the transistor. The top, shown here in light green, this is called a gate insulator. And the important thing is that it's an insulator. In a silicon transistor, this would be oxidized silicon, SiO2, or quartz. The dark blue layer is the channel. And the important thing about the channel is that it's normally conducting. Okay? So this is a heavily doped semiconductor. For example, it might be an N-type semiconductor. If the channel is conducting, then we could pass a current, say, between the source and the drain by applying a voltage. And then the bottom here is called the substrate, and this is non-conducting. Although in a silicon transistor, if the channel were N-type, then the substrate might be doped slightly P-type, so that we'd have a PN junction here that wouldn't allow any current to pass. The important thing is that any electrical current is fixed. It has to run through the channel if it's going to run at all. Okay? Well, let's see how this can work as an electrical switch. Oh, I forgot the most important thing. The last contact. So this is a 3-contact device, just like the triode. We had the source and the drain, which are connected by the channel, but we have one more contact, the gate contact, which is a metal layer on the surface of the semiconductor. So this is a metal oxide field effect transistor, or MOSFET, metal oxide semiconductor field effect transistor. Okay, let's see how this works. So the transistor has 2 states, on or off. And we're describing something called a depletion mode FET, but don't worry about that right now. Let's just imagine it in the on state. In the on state, there are lots of free electrons in the channel, so a current can easily pass from the source to the drain. Okay? This is like a resistor with a rather low resistance. We might ensure that by positively biasing the gate. That would mean electrons would be pulled into the channel from the source and the drain connectors, or they might be there already. In any event, this is the state when the transistor is on. Now imagine we apply a large negative bias to the gate. If we apply a negative bias to the gate, it will repel electrons. So the electrostatic potential here will become a barrier for electrons to flow from the source to the drain. In essence, electrons are repelled by the negatively charged gate, and they're pushed out of the semiconductor and into the source and drain connectors and into those wires. And because semiconductors, even heavily doped semiconductors, have a rather small concentration of electrons compared to a metal, it's possible to do this even with a moderately large gate voltage. And in this way, we can switch the semiconductor from off to on by applying a voltage. So you can see this works in much the same way as the triode does. Okay? It's actually a rather simple device.